How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your Chapter 17, Section 3 notes, all over heat and changes of state. So we have heats of fusion and solidification. All solids absorb heat as they melt to become liquids. The gain of heat causes a change of state instead of a change in temperature. The temperature of the substance undergoing the change remains constant. So what that means is that as an ice cube is melting, right as it's changing from a solid to a liquid, its temperature remains constant. It isn't changing until after it's a liquid. Then the temperature will continue to change. The heat absorbed by 1 mole of a solid substance as it melts to a liquid at a constant temperature is the molar heat of fusion, or delta H sub FUS. The molar heat of solidification, or delta H sub SOLID, is the heat lost when 1 mole of liquid substance solidifies at a constant temperature. The quantity of heat absorbed by a melting solid is exactly the same as the quantity of heat released when a liquid solidifies. So the delta H of fusion equals the negative delta H of solidification. The melting of 1 mole of ice at 0 degrees Celsius to 1 mole of liquid water at 0 degrees Celsius requires the absorption of 6.01 kilojoules of heat. And here's how we would write that heat of reaction. The conversion of 1 mole of liquid water at 0 degrees Celsius to 1 mole of ice at 0 degrees Celsius releases 6.01 kilojoules of heat. And that reaction is going to look like this, because remember, this is the exothermic process. So let's do a calculation. How many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat are added? So we have our heat of reaction here. So remember, we just always start with what we know. And what do we know? We have 2.25 kilojoules of heat. And we eventually need to get to grams of water. So if we look at the information we have a unit conversion right here. We can use the delta H of fusion. So that's 6.01 kilojoules per mole. Because remember, for 1 mole of solid H2O to convert to 1 mole of H2O, it requires 6.01 kilojoules. So now that we're at moles, we can get to grams, because we know that the molar mass of water is 18.016 over 1 mole of water. So mole cancels with mole, kilojoule and kilojoule. We're left with grams of water. When we calculate this out, we get 6.74 grams of H2O. So we also have heats of vaporization and condensation. A liquid that absorbs heat at its boiling point becomes a vapor. The amount of heat required to vaporize 1 mole of a given liquid at a constant temperature is called its molar heat of vaporization, or delta HVAP. And over here in this chart, these are just some common delta heat of fusion and delta H of vaporization for different common compounds. Condensation is the exact opposite of vaporization. When a vapor condenses, heat is released. The molar heat of condensation, or delta HCOND, is the amount of heat released when 1 mole of vapor condenses at its normal boiling point. The quantity of heat absorbed by a vaporizing liquid is exactly the same as the quantity of the heat released when the vapor condenses. So, just like delta heat of fusion and delta heat of solidification, these are opposites. So here, that just kind of shows them in a graphical way. The delta H of vaporization increases, therefore the delta H of condensation goes down. And the same works for the delta heat of fusion and the delta H of solidification. Just showing the different changes of state that we'll be working with as we go through this chapter. So since we can look at these changes in state, we have what's called a heating curve. A heating curve graphically describes the enthalpy changes that take place during phase changes. So as you can see, we start down here in the solid region, the temperature increases until right here, that is when we have the melting point. So along this line, the temperature remains constant, but that is where we see the solid melt to a liquid. And then as we increase the temperature, we reach this next line, which is our delta H of vaporization. And this is where we see the boiling point. And again, the temperature is constant as the liquid changes into the vapor phase. So we can do another calculation here. How much heat in kilojoules is absorbed when 24.8 grams of H2O liquid at 100 degrees Celsius and 101.3 kPa, which we know those to just be STP, is converted to H2O gas at 100 degrees Celsius. And it gives us our delta H of vaporization. So again, we just start with what we know. We have 24.8 grams of H2O, and we are going from a liquid to a gas, so that's vaporization. And so our conversion factor is 40.7 kilojoules per mole. But we're in grams, but that's no problem because we know how we can get to moles of water. We go through our molar mass. Now that we're in moles on top, we can use our conversion factor here because we know that 1 mole is equal to 40.7 kilojoules. Our correct units are going to cancel out here. We're left with kilojoules. We multiply that through and we have 56.0 kilojoules of heat. So that's the amount of heat that is absorbed by liquid water to change state into the vapor phase. So we also have heats of solution. So during the formation of a solution, heat is either released or absorbed. The enthalpy change caused by the dissolution of 1 mole of substance is the molar heat of solution. A practical application of an exothermic dissolution process is a hot pack, or those hot hands, those little packs that you might put in your gloves if it's cold out. So this is the reaction that is occurring in those hot hands or the hot pack. It's calcium chloride solid, and it's breaking down into Ca2 plus ions and 2 Cl minus ions. And the delta H of the solution is negative 82.8 kilojoules per mole. So what do we know about negative delta H's? That implies an exothermic process, which means heat is released, which is why shaking those packs or combining these into breaking up the ions releases heat and allows us to warm up our hands. So we can calculate the enthalpy change in a solution formation. So how much heat in kilojoules is released when 2.5 moles of sodium hydroxide is dissolved in water? And they give us our delta H of solution. So again, we just start with what we know, 2.50 moles of NaOH. We're going to use our delta H of solution to get to kilojoules. So 1 mole is equal to negative 44.5 kilojoules. And we cross off our units and we multiply through and we get 111, and that's negative because this is an exothermic process. So when we dissolve 2.50 moles of sodium hydroxide in water, negative 111 kilojoules is released. So in review, the quantity of heat absorbed by a melting solid is exactly the same as the quantity of heat released when the liquid solidifies. That is, the delta H of fusion equals the negative delta H of solidification. The quantity of heat absorbed by vaporizing liquid is exactly the same as the quantity of heat released when the vapor condenses. That is, delta H of vaporization equals negative delta H of condensation. During the formation of a solution, heat is either released or absorbed. And that's it for section 3. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.